welcome to the Might Ramble podcast.
Ron, tell us about that.
Not two, not three, not four, not five.
Now I am become death, the destroyer of worlds.
From this distant vantage point, the Earth might not seem of any particular interest.
This is Mitchell Penningroth. Thank you for checking out the audio version of my piece. I work from the intersections where biochemistry, neuroscience, recovery, and human performance meet. My aim is to translate my lived experience and scientific background into tools and perspectives that others will find useful, amongst other near and far-reaching topics that may come up. Through the radical honesty often found in recovery from substance abuse, blended with the objectivity of scientific inquiry, I work to illuminate how trauma, addiction, and resilience are wired into the brain and body, and how they can be rewired. Each piece is a small step toward a long-term vision, building a space that unites research, training, and community for deep, lasting change, helping people both directly and indirectly reclaim or optimize their lives. Subscribe to follow along and help me build an audience that will be useful in putting this vision into action. On the Boundary of Knowledge, originally published on my Substack. Working at the boundary of knowledge is challenging. The boundary exists for a reason. Beyond it lies a vast, tangled unknown, with no guarantee it can even be grasped by the human mind. Evolution's slow chisel has shaped us to fit the universe, not the universe to fit our understanding. Take my experience with quantum mechanics, for example. By the time I reached it in my undergraduate studies, I had years of prerequisites behind me: algebra, trigonometry, introductory calculus, multivariable calculus, linear algebra, differential equations, thermodynamics, general chemistry, statistics, and general physics come to mind. Up to that point, my problem-solving intuition usually lined up with reality. If I reasoned carefully and knew my stuff, I land in the right place. But in quantum mechanics, wherever my intuition pointed, I was pretty much always wrong. I worked hard, I stayed engaged, I asked questions. Effort was not the problem. I frequently went to the professor's office hours, and after one long explanation of how I thought a problem should go, he simply said, "You are entirely off base." He was right. And that became the pattern. The rules of the quantum world, and interestingly, of the cosmic scale too, don't map neatly onto how we experience daily life. On those edges, our ordinary compass often fails, though there are certainly individuals more capable and inclined to work with the quote-unquote existentially weird parts of the universe than I am. This is one aspect of why the boundary of knowledge exists. Not because we aren't trying hard enough, but because reality itself, at times, resists our intuition. There is also uncertainty in many things we think we know. Much of what we take as established is less secure than it appears. A single discovery can cascade through connected fields, reshaping theories the way a stone tossed in water disturbs every ring that spreads outward. What once seemed settled suddenly has to be re-examined. A real-world echo of this lies in a case from the University of Minnesota, my alma mater. In 2006, neuroscientist Sylvain Lesne and his team published a highly influential Nature study, pinpointing a compound called amyloid beta 56 as a primary cause of Alzheimer's disease. It sent shockwaves through the field. Hundreds of millions in funding flowed to follow up research. But in 2022, sleuths uncovered that key Western blot images in the paper were digitally manipulated, spliced, duplicated, even erased. For those unfamiliar, a Western blot is basically a lab test that separates proteins and makes them visible on a film, like fingerprints on a crime scene, so scientists can see if a specific protein is present and how much of it there is. After a prolonged investigation across more than 20 papers, the original study was formally retracted in 2024, and Lesne resigned effective March 2025. Critics, like Elizabeth Bick, called the manipulation a severe breach of scientific integrity, warning that it had led other researchers astray and created false hope for patients and families. Many labs have been chasing shadows, as has often been the case as it concerns Alzheimer's and amyloid beta. For a more historical example of the uncertainty of our knowledge, consider just a portion of Albert Einstein's preposterous set of discoveries in the early 20th century. Before Einstein, Newton's laws assumed that time and space were absolute, the universe a static backdrop. Think of this as a picture with fixed height and width. taking the same amount of time for anyone's eyes to scan across. And then Einstein came along. Einstein instead showed the picture is printed on a flexible sheet. Stretch or tilt it, and the height and width change. Even the time it takes to scan across the sheet depends on how the sheet is warped. Space and time aren't rigid backdrops at all, but a single fabric, spacetime, bending and flexing with motion and gravity. This brings to mind the interstellar scene, where the crew must escape the water world because of time dilation. To simplify, time dilation is the phenomenon in which time runs more slowly near a very massive object, like a black hole, than it does farther away.
What are you waiting for? Let's go. Go, 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 go. 7 years per hour here. Let's make it count.
Technically, the same effect would occur if you were standing near the Great Pyramids in Egypt. Your clock would run ever so slightly slower than someone farther away, though the difference would be so minute as to be imperceptible to us. There are other factors that shape where the boundary of knowledge sits. For example, consider two people. Person A is 50 years old and has lived with depression since early childhood, while person B is also 50 but developed depression after a concussion at age 30. How might the neurons in person A's brain differ from those in person B's? Is their depression truly the same? Ethically, there are limits to how we can study this. Entering a living person's brain to collect, stain, or image neurons directly would compromise their ability to function. For now, the boundary of knowledge there is guarded, constrained by both ethics and the limits of current technology. More broadly, this is to say the boundary isn't set by nature alone. It's also shaped by what we choose to prioritize. In the late 1950s, humanity decided it was of vital importance to reach the moon, a goal that culminated on July 20th, 1969, when Neil Armstrong stepped onto the lunar surface and declared,
It's one small step for man, one giant leap for mankind.
Today, at least 98% of the moon's surface has been mapped with high-resolution methods. By contrast, only about 25% of Earth's ocean floor has been mapped to similar standards. Even more striking, at depths below 200 meters, where sunlight no longer penetrates, more than 99% of the seafloor remains entirely unexplored. If humanity in the late 1950s had decided it was of vital importance to thoroughly map and understand the oceans, do you think we would still have only 25% mapped well in 2025? My point is, the boundary is not arbitrary. The universe does not yield itself easily to our understanding, and we are not built with the hardware to follow it everywhere on our own. That's why we invent tools, microscopes, telescopes, particle accelerators, to extend our reach. At the same time, we still have real agency in deciding where to push the boundary out further. Pushing that boundary, the task of research scientists, usually entails countless failed experiments, long cycles of troubleshooting, and many hours of strained reconciliation between what we know, what remains uncertain, and how fragments of knowledge might be pieced together to reveal the next sliver of the unknown. And when such a sliver is captured, the work is not finished. New questions arise about the new sliver's limitations and uncertainties, and how its incorporation reshapes the boundary itself while reverberating back onto what was previously known. Importantly, scientists rarely push into the dark blindly. Instead, they take a new question and anchor it to ones we already know how to answer. For example, asking, what sugars are in a giant squid? May sound unapproachable at first. But by linking it to established biochemical methods and knowledge of sugars in other organisms, such as an apple, the unknown becomes less opaque. It's like going to a new grocery store for the first time. How do you figure out where things are? You probably start by recalling how your old grocery store was laid out. Fruits in one section, bread in another, and use that map as a guide while you explore the new one. Add up hundreds of thousands of years of venturing a little further into the unknown, and you get the arc from building a fire to splitting the atom. Research is the act of standing on a scaffold, comparing what we do not yet know to something we already understand, and pulling a sliver of the unknown into the light of the known. Each slice of the unknown is hard-won. The irony is that every new piece of knowledge only expands the bubble of the known, and with it, the boundary. The more we know, the more we realize how much remains unknown. Specialists train for years to navigate the complexity at the boundary as fluently as possible, but for most people outside a given niche, the technical language and fine-grained experiments are nearly impenetrable. Within the life sciences, though this likely applies elsewhere as well, much of the work that shapes our understanding of life and of ourselves rarely reaches the broader public in a clear, meaningful, and timely way. Expertise that cannot be communicated is like a locked vault that endlessly refills itself. Impressive, sure, and useful if you hold the key, but far less valuable than it could be if its contents were made accessible to others. What say you, supply and demand? If relativity showed us that even time and space bend under certain conditions, aging shows us something similar on a more personal scale. Our bodies, too, warp and change in ways that defy our everyday intuition and insight. Science has revealed much about this process, yet the picture rarely travels far beyond the lab. We all recognize the obvious surface markers: wrinkles, gray hair, stiffening joints, fragile bones, slower reflexes, and eventually the failure of some crucial system. But beneath these familiar signs of aging lie hidden mechanics every bit as unforeseen as the physics behind a black hole. If tissues change, then the cells making them up must be changing. And if cells change, then the molecules and structures within them, mitochondria, chromosomes, proteins, and so on, must also be changing. What we see is just the tip of an iceberg with a finely pixelated mass hidden beneath. That hidden bulk is hard to measure directly or tease apart, yet it ultimately dictates the whole trajectory of aging. The full picture is still being assembled. Aging is complex, multifaceted, and its precise definition can be slippery. Still, certain pieces of the puzzle are becoming clearer, along with hints of what we may be able to do with that knowledge. Personally, I think of aging as a health condition we all have in common. To give an example of locked vault knowledge, in C. elegans worms, a model organism in aging research, they're about 1 millimeter in length for scale here. A brief heat shock in early life extends lifespan, whereas the same treatment later has little to no effect. The stress of the heat activates heat shock proteins, molecular repair systems that cells deploy to keep proteins from misfolding and chaos from spreading. What's remarkable is that we can track this process fully, apply heat, measure the change of a molecular switch within the worm, track the surge of heat shock proteins, and then observe the lifespan outcome. Stimulus in, measurable effect out. Clear, objective, and tangible. There is no mystery, and that clarity is astonishing. By analogy, it's like briefly exposing a new house to flame in order to fireproof it against future burns. But with an old house, the same treatment would not be helpful. To change topics a bit, maybe it's just me, but health advice often feels fuzzy. To be clear, evidence-based providers are usually excellent at what they do. That's not what I'm questioning here. And yes, other forms of medicine can carry value as well. I mean this more generally. You talk to one person in your life, then another, and the advice starts to clash. One says you should cut out carbs. Another says carbs are fine, but seed oils are the real problem. And another insists it's all about intermittent fasting. The information gets murky. The promised outcomes are usually vague. You'll feel better, support wellness, fix your gut, align your energies. What does that even mean? I'm encountering this a lot in Austin, Texas. Optimize health, and so on. Rarely do we get a perfectly clean chain to point to. Do A, then B happens, which leads directly to C in an objective, fully deterministic way. Providers certainly work with cause and effect, but often at a different zoom level than research scientists. Researchers may isolate variables under controlled conditions to map out precise mechanisms and carefully define slices of reality. Providers, by contrast, must translate that evidence into the care of a living, breathing human being. Someone with multiple conditions, genetic quirks, personal beliefs, side effects, financial limits, and family stressors. In other words, providers operate within the messy complexity of real life. And then, in the research sphere, every once in a while we get worms in the vault, cases where cause and effect align with striking precision. The takeaway from the heat shock example is that sometimes stress preserves. This principle is called hormesis. Low doses of a stressor or toxin trigger an adaptive response that ultimately makes the organism more resilient, both in general and to higher, potentially harmful doses of that same stressor. Some stress, when experienced in the right dose and at the right time, is essential for building resilience. Aging research reveals this at the molecular level, where the picture is clearer and leaves less room for interpretation. Practices like exercise, fasting, or temperature stress are examples of hormesis in action, although our understanding of what exactly these practices do in humans at the molecular level remains incomplete. My aim in future pieces is simple: outline, in plain language, what we currently understand about what it means to age at a Zoom level usually inaccessible to outsiders. It won't cover every detail, but it will provide a framework and can serve as a guide to exploring some of the components more in depth if curious, an entry point into the biology of aging of sorts. This approach will not be exclusive to aging long term, but I thought I'd use it as a starting point.